All right, so let's take a look at geometric sequences and series. We've already talked about arithmetic sequences, and that's when we have differences of the consecutive terms. For geometric series, we have ratios of consecutive terms. And so basically, our common ratio we use with the number r, or the letter r represents a number. So let's take a look at example 1. Find the common ratio for the geometric sequence 10, 20, 40, 80, 160, and then 5 times 2 to the power of n. So to get from 10 to 20, we multiply by 2. From 20 to 40, multiply by 2. 40 to 80, multiply by 2. Hopefully you see the pattern here. Our ratio is 2. Okay, you can also see that in the geometric sequence expression, because that is the base of our power term. Okay, so let's take a look at the formula for the nth term of a geometric sequence. All right, so we have a sub n equals a sub 1 times r to the n minus 1. Okay, so we can use that basically for to get each consecutive term, we want to multiply by r. All right, so we want to find the 9th term of the geometric sequence whose first term is 4 and whose common ratio is 1/2. So a sub 1 is 4 and r is 1/2. So we're just going to plug that into the formula. A sub n equals a sub 1 times r to the n minus 1. So a sub n equals 4 times 1/2 to the n minus 1. So there is our formula, okay? And we want to find the 9th term. So we are going to plug 9 in. So a sub 9 is equal to 4 times 1/2 to the 9 minus 1. So that equals 4 times 1/2 to the 8th. And so when you raise 1/2 to the 8th, you get 1 over 256. And then when you multiply 4 times 1 over 256, you get 1/64. So that is the 9th term of this sequence. So let's take a look at example 3. The second term of a geometric sequence is -64. So a sub 2 is -64. The 5th term is 1/8. Okay, so we want to find the 7th term. Well, let's see if we can figure out what the formula should be based on the information that we have. Okay, so we know that we can do a sub 5 is going to equal a sub 2 times r to the 5 minus 2. Okay, so we can figure out what our r squared is going to be by using that. So a sub 5 was 1/8. A sub 2 is -64. And then r times r cubed. Okay, so we're going to multiply both sides by 64. I'm sorry, we're going to divide both sides by 64. And so we get -1 over 512 is equal to r cubed. And then when we take the square root of both sides, we get -1/8 is r. Okay, so now we can find the general form for this sequence, right? So we can say a sub 2 is equal to a sub 1 times r to the 2 minus 1. Well, we know a sub 2 is -64. We want to find a sub 1. R was -1/8, and 2 minus 1 is just 1. So in order to get rid of the -1/8, we multiply by -8 on both sides. So a sub 1 is 512. Okay, so now we know that our general form is a sub n equals a sub 1, which is 512, times r, which is -1/8, to the power of n minus 1. So if we want to find the 7th term, a sub 7 is going to equal 512 times negative 1/8 to the power of 7 minus 1. And so we can multiply negative 1/8 to the power of 6, and we get 1 over 262,144. And then when you multiply 512 times that fraction, you get 1 over 512. Okay, another way you could do that problem is you could do a sub 7 equals a sub 5 times r to the, times r to the 7 minus 5. Okay, and so you would have a sub 7 equals a sub 5, which is 1/8, times 1/8 to the 7 minus 5, which was 2, and then you have 3 of those 1/8 being multiplied together. Oh, and that was negative 1/8. And so then when you square that, you get a positive 1/64 times 1/8, and you still get 1 over 512. So there's a couple different ways that you could do that problem. It just depends on how you want to do it. All right, let's take a look at the sum of a finite geometric sequence. Remember that we could do this with arithmetic sequences, and now we just have a different formula for geometric sequences. Okay, and so our formula is a sub 1 times 1 minus r to the n over 1 minus r. So the first thing we want to do is identify the pieces, right? So in this problem, a sub 1 is 1, right? Because there's nothing that 4 is being multiplied by. And so we know that our common ratio is 4, and then the I is just n. Okay, and so we want to plug in our values. And so if we look at our general form, we've got a sub 1 times 1 minus r to the n over 1 minus r. All right, so a sub 1 was just 1. Our r is 4, and n is 7 here, over 1 minus 4. Okay, and so we get negative 16,383 over negative 3. And when you divide that, you get 5,461. So that would be the sum of that finite series. All right, now let's take a look at the sum of an infinite series. The formula is just a little bit different. This time, there is no 1 minus r to the n in the problem. So it just becomes a sub 1 divided by 1 minus r. So it's a very similar formula. We're just removing that numerator from the original formula, from the finite series formula. All right, so for the first example, we know that a sub 1 is 7. We know that r is 1/3, and we're just going to plug those into the formula. So a sub 1 over 1 minus r. So 7 over 1 minus 1/3, which is really 7 over 2/3, which is the same thing as saying 7 divided by 2/3, which is the same thing as saying 7 times 3/2, which is 21 halves. And to give an exact answer, you would leave it as a fraction. Let's take a look at the second example here. So we know that a sub 1 is 5. And we can rewrite this as 5 times 0.1, and then 5 times 0.01, and then 5 times 0.001, and so on. And so we know that our r and this is the same thing as 0.1 squared, 0.1 cubed. So we know that our R is going to be 1/10 or 0.1. So we can use our formula 5, a sub 1, over 1 minus R, which was 0.1. So that's 5 over 0.9. And then if you multiply, if we want an exact answer, if you multiply by 10 over 10, that's going to get rid of your decimal in the denominator. And so we end up with 50 over 9. And that is our answer if we want to give it an exact form, which we do. All right, let's take a look at the very last example. And this is a good example of where it could be used in the world. A deposit of $100 is made on the first day of each month in a savings account that pays 6% compounded monthly. Find the balance of this annuity after 4 years. All right, so this is a compound interest problem. So remember that our amount is equal to the principal times 1 plus the rate over the number of times it's being compounded times the n, and then times the, or to the power of n, the number of times it's being compounded, times n, t, which was the number of years. So if we want to look at the 48th year, we know that the principal is 100 and the rate was 0.06. It's being compounded monthly, so there's 12 months in a year. And so this was after 48 times of being compounded, so that was 4 years. That's where the 48 came from. Okay, and so this is month number 1, right? And so if we want to find the very last month, we're going to go down to a sub 1, where there's 1 month left, and that's going to give us 100 times 1.005 to the power of 1, because it's the very first term, and so there haven't been any years. And so this is the last month. All right, so we want to find the balance of the annuity after 4 years. So we have our formula. Oh, that's not equals. This is just copied from the previous one. All right, so after 48 months, we have 100 times 1.005. That was our starting point, right? And then we're going to multiply by 1 minus 1.005 to the power of 48 over 1 minus 1.005, because the R is 1.005. It's a different R this time. It's not the rate. This is our common ratio. So keep in mind that this R is the common ratio, not the interest rate. Okay, R stands for something different this time. And so when we multiply 100 times 1.005, we end up with 100.5. And then if you plug in the fraction into the calculator, you end up with 54.0978322. And then when you multiply that, you get about $5,436.83. And that is the balance of the annuity after 4 years.